of the dominance duration distribution. It's like a gamma distribution or log normal distribution. Okay? And the qualitative or the conceptual model of this is that there are two populations of neurons somewhere, one corresponding to one percept, the other corresponding to the other percept, and they're competing with one another through, say, inhibition. So one population becomes dominant and steps on the other population, and then somehow there's a switch, and only one of them can be active at any one time. It's mutually exclusive through this property of mutual inhibition. Okay? And then the question is, how do you get the switching? Okay? So people typically rely on some kind of slow negative feedback process. Maybe the neurons get tired of firing. It's called spike frequency adaptation. Or the synapses get tired of sending transmitter or get depleted of transmitter, called synaptic depression. Either one of those is a slow negative feedback, time scale of second or something like that. The typical mean durations here are a few seconds. Okay? So what I'm going to talk about are first pose some oscillator models, okay, in a noise-free environment, perfectly periodic oscillations, okay. Mechanism will be mutual inhibition and spike frequency adaptation or synaptic depression. We'll add some noise and get randomness to the durations, look more or less like those distributions. There's going to be something that these models don't do. Okay, so we went to another phase of models. So another possibility, of course, is that the noise just doesn't perturb a periodic oscillator, but the noise is critical to create the alternations. We're talking about a bistable system here. Suppose the parameters are such that the system will not oscillate without noise. Okay, one population becomes dominant. It doesn't adapt enough to lead to switching. So it could just stay bistable. But noise, it could just stay one on. Noise could kick the system to the other state. A little bit of adaptation. Noise could kick the system this way. Okay? So this is called a tractor-based, noise-driven oscillation. Okay, so we'll pose a model like that. A phenomenological model like this is a physicist's double well potential, in which the wells can jiggle a little bit, not enough to completely cause a switch, but the noise kicks you across an energy barrier. Anybody heard of a double well potential? Okay. So we'll then look at these two frameworks and compare them to the statistical data that we get from the experiments and sort of place our bets about which mechanism we think it makes more sense. Okay. Okay, so it's a very simple model. This is not a detailed biophysical model of a network of neurons interacting with each other. The principal variables here are the firing rates in the population. So these are called firing rate models. Classical framework is Wilson-Cowan-like models. Has anybody heard of Wilson-Cowan models? Okay, so the variable is firing rate. So the models take the form of this. So here's the schematic. Population 1, population 2, firing rate R1, firing rate R2. Coupled, the black dot means inhibition. And this means negative feedback. Slow negative feedback. Okay, so, oh no, that's not good. That's going to happen again. So this is the form of the dynamics. Okay? So this says that the firing rate obeys a simple first-order dynamical equation. S is the input-output function of this network. For fixed input, the firing rate wants to go to a level S. Okay? And as the input strength goes up, the firing rate goes up and saturates. And the firing rate R goes to that level S with some time constant tau. Tau is the recruitment time in the population. Okay? It's not the membrane time constant. It's not a direct biophysical time constant. It's a complicated mess of many different biophysical things. Okay? So what is the input to population 1? The input to population 1 is the sensory input, I1. Okay? It's being inhibited by population 2, and we're saying the inhibition weight is beta, and it depends on the activity of population 2. And this is the negative feedback. The negative feedback variable is A, and its strength is phi. Okay? And so here's the dynamical equation for the adaptation variable. The adaptation variable, again, has a generative property. It is generated by firing rate. Okay? And F has a similar shape to S. As the activity goes up, the adaptation goes up. It's an activity-dependent adaptation. Its timescale tau A is much bigger than the recruitment timescale. So this is the slow negative feedback. Okay? So each population has two variables, the firing rate and its negative feedback. Okay? So altogether there's 4 equations for this system. Okay, so usually when I tell people about neural oscillators, I pull out my Bible and I say, to get neural oscillations or excitability, you have to have autocatalysis, fast autocatalysis, and slow negative feedback. Something to push the system up and something to pull it back down slowly. This is how you make oscillations. Okay. Well, there is, usually when we talk about recurrent network models, okay, the autocatalysis is coming from excitatory coupling. Okay? Excitatory to excitatory coupling. There's no recurrent excitation in this model. Okay? On the other hand, there is positive feedback. Because I'm inhibiting somebody who's trying to inhibit me. So minus times a minus is a plus. Okay? So there's positive feedback on the fast time scale and negative feedback on the slow time scale. So you get oscillations because of that. Okay. This framework has been around for a long time. This is a classical framework coming from some of the original models that people talk about in terms of central pattern generators, neural architectures that drive alternating muscle groups for locomotion, for respiration, for chewing, whatever. Okay? Mutual inhibition and slow negative feedback. So some of the things we say might have to be interpreted that way. So it's easy to get this model to oscillate. Okay? Population red is on, population blue is off. It's recovering from adaptation. At some point, there's a switch. Okay? Perfectly periodic. There's no noise in the system. These are the variables for the red population. Firing rate is high. The negative feedback is building up. This is the adaptation variable A1. Adaptation gets large enough, the activity starts to drop, and suddenly there's a switch. Okay? Population red is off, and it's